for making our stay here very easy. And thanks for giving me the opportunity to present. So for those who don't know me, my name is Vassilios Dallas. I'm a Newton Fellow at the Applied Mathematics of the University of Leeds. This is some work that I did in collaboration with Alexandros Alexakis while I was at the Colonel Marie Superior as a Marie Curie Fellow. So unlike in hydrodynamic turbulence, where usually there is, you know how it works?
Left and right. Have you plugged it in?
This is okay.
Oh, you haven't included the...
Oops.
Okay.
Just continue and then... Yeah.
It should be okay. Never mind, I will do it from the, from the computer. So unlike in hydrodynamic turbulence, where we have the usual Kolmogorov theory with the k-5/3 spectrum, in MHD there is a zoo of inertial range phenomenologies. So you can see there are phenomenologies for strong MHD turbulence and weak MHD turbulence, where basically the alpha waves are important, where they make the cascade weaker, and we can have very different scalings for the dissipation, the velocity, and finally different energy spectra. So the motivation of this work was a paper by Annick Pouquet and co-workers in 2010, where basically the result was that they had three different initial conditions and that led to three different spectra. They observed the k-2 spectrum, which they interpreted as weak turbulence. They found a k-5/3 spectrum and a k-3½ spectrum, interpreted as Kolmogorov erosion of Kreiknan. So in their study, basically all the runs were not forced. So we have decaying simulations. All the initial conditions have a compartition of energies, and they ensured that all the helicities are zero. So in this talk, we are interested at the time where the dissipation is maximum. This is the time where the largest scale separation occurs in our flow. And this is the time where we are interested. So these are the three different configurations they used. The blue indicates the velocity, the red indicates the magnetic field. So they had one case where basically the current was parallel to the wall, so they called that case insulating case. In this case, they observed at T peak, this is the time, again, that the dissipation rate is maximum. They observed the k-2 spectrum, and they also observed that the magnetic field was much greater than the magnetic energy was much greater than the kinetic energy. For the alternative insulating case, again, the current is parallel to the faces. They observed the k-5/3 spectrum, and the magnetic energy was less than the kinetic. And finally, for the conducting case, where basically the current is perpendicular to the faces, they observed the k-3½ spectrum, and there the kinetic energies were of the same order. Just to say a few more details about the weak turbulence theory, which gives the prediction for the k-2 spectrum, which they also observe in these simulations. However, we're not sure if this is the interpretation. So basically, we have for weak turbulence, usually there is a background large-scale magnetic field, and traveling alpha waves are traveling along the magnetic field lines. And there, in this case, we define an alpha time scale as L perp over B0, and the nonlinear time scale, which is the eddy turnover time, as L perpendicular over UL. And for weak turbulence theory, the alpha time scale is much smaller than the nonlinear time scale. So basically, the dissipation is modified by this ratio. So we get the dissipation to scale like this, and then the energy, the velocity as L perp to the 1/2. So then the spectrum will give us a k-2 spectrum for the k perp. However, in the simulations, there was no large-scale magnetic field. What they observed, though, was that EB was about 4 times EU. So they assumed that the magnetic energy plays locally the same role as B0. So, however, the condition that EB is much greater than EU alone is not necessary to give weak turbulence. So there are more conditions that are necessary, and particularly that tau A is much less than tau nonlinear. Therefore, we conjecture that the K-2 scaling can possibly manifest from other different conditions than weak turbulence. Here I'm showing you the energy spectra that we computed for the insulating case, so for this case here. And here are the compensated spectra for different exponents for the magnetic energy and the kinetic energy. So you can see the -2 is clearly there. However, for the kinetic energy, we don't really have a power law. So we're going to concentrate what happens for the magnetic field. Another reason that we choose to study the -2 spectrum is that you can distinguish it much clearer than the 5/3 and the 3/2. You can see if you compare these three exponents, you can see that the difference between the three exponents is much clearer for the -2 power law. Because, of course, the scale separation in DNS is limited by the computational expense. And a striking result is by the spectra that they were measured from Voyager 2 at 5 astronomical units. And here they show the magnetic energy spectrum and the kinetic energy spectrum. And you can see that the spectra span almost 4 decades of order of magnitude. And really, you cannot really distinguish between 5/3 and 3/2. So we focus on the -2. So this is how the flow looks at the maximum dissipation, when the dissipation rate is maximum. You can see that there's a structure in the flow due to these Taylor-Green symmetries. And actually, here what I'm plotting is the current density. Here on the right-hand side, I'm just showing you the components of the magnetic field. So this component is the Bx component, this component is the By, and here is the Bz. So if we just look at the top face and we take a profile across here, what we see is that the Bz component is actually like a discontinuity. So from there, you can easily, we all know that basically if we can represent the Bz as a Heaviside function, if you take the derivative of that, that will give you a delta function. And from there, if we integrate from the definition of the delta function, we can actually integrate in spectral space, and we can find that the magnetic energy is basically a K-2. The K-2 also appears in the Berger's turbulence, so it's like having discontinuities. It's the same kind of phenomenon. Of course, this was just the Bz component. So to be more precise, what we did is we tried to filter these structures. And in order to see if the -2 comes from these very sharp current sheets or from the background flow. So what we did is we did the following decomposition. So we have a high-pass filter and a low-pass filter. And then we reconstruct the B high-pass filter in this way and the B low-pass like that. And we recalculate the spectra. So what we do that for different thresholds. So basically, we do a J cut over J max 0%. That will give us, of course, the total ohmic dissipation, and that will be, the whole volume. So we take just the 5% of the J max. That will give us 92% of the ohmic dissipation. But remarkably, this 92% of the ohmic dissipation is concentrated only on the 8% of the total volume of our box. So these sharp structures seems to have all the ohmic dissipation there. Then, as we increase the filtering, you can see that there is less and less dissipation, and of course, this is concentrated to less and less volume. So here, I'm just showing you the compensated energy spectrum with k², and you can see that we increase here the filtering, and you can see that these narrow structures give the -2 spectrum. But here, I think is more striking that we just do the low-pass filter. So basically, we have only 8% of the dissipation and 92% of the total volume. and that gives us a power law that is far away from 2. So it is clear that the -2 spectrum comes from these discontinuities. So okay, now the questions that we asked are the following. Are there more general classes of flows where the initial conditions give a -2 power law spectrum? And if so, are there classes of universality, or is there a universal power law for the high Reynolds number limit? So I will try to address this question. So what we do is we do the standard 3D DNS for homogeneous decaying MHD. There's no, again, magnetic flux. This is a standard equation that we all know. The only peculiarity here is the following. This Taylor-Green flow has the following property. The velocity at t equals 0. Yeah? The initial condition was that. The velocity was the curl of the magnetic field, and the magnetic field was equal to the minus curl of the velocity. So what we do for our initial conditions, we consider random initial conditions. So we randomize our wave numbers k1 and 2 with random phases. And we impose j proportional to u or b proportional to omega. What I will show, the results are almost the same, but I will concentrate just on this case, on j proportional to u. So at time t equals 0, we normalize such that EU and EB is equal to 0.5, and all the helicities are 0, and the magnetic Prandtl number 1. So here what I'm showing is two sets of data. The circles are our data, and the triangles are the data by Menini and Pouquet from 2009. Their DNS at the time was the highest MHD DNS of homogeneous turbulence, was 1,500 cubed. And what they were showing, basically, that the dissipation as Reynolds number increases becomes finite for high enough Reynolds number, and this is the dissipation anomaly well known in turbulence. However, for our data, the normalized dissipation doesn't seem to reach an asymptote, even for a 2,000 cube simulation that we managed to do at the time. So, is there different we seem to have different high Reynolds number asymptotics with no asymptote for the dissipation rate, even for this high RE lambda. Here, what I'm showing is basically I'm plotting the Kolmogorov scaling, which is the RE lambda proportional to Reynolds number to the 1/2. And you can see that for high enough Reynolds number, the Menini and Pouquet data, they get to this scaling. However, our scaling seems to be a bit different. So RE lambda seems to scale with Reynolds number to the 2/3. So do we have some non-classical scaling, or are we going to reach this regime if we go further in Reynolds number? Let's see. So usually when we visualize turbulent flows, we see intense dissipative structures, randomly oriented. There's a large population of them in a large range of scales. And usually in hydrodynamic turbulence, they have the shape of tubes. In MHD turbulence, they have the shape of current sheets in general. However, in this case, you see that there is a huge, this is the current density, there's a huge current sheet sitting in the middle of the box, almost spanning the size of the box. You don't see this kind of mess that you usually see. So what is this? So let's see in more detail what happens. So this is a 2D cut of the box. So I'm going to show you for different Reynolds numbers what happens. So for RE lambda 95, you can see the current sheet in the middle of the box. As I increase the Reynolds number, there seems to be some type of Kelvin-Helmholtz type instability being created here. Then if I increase further, you can see that the current sheet curls even further. And for the highest Reynolds number, we see some type of reconnection happening, and a smaller scale is appearing. So let's see what is the spectra. So here I'm just showing the energy spectrum compensated by k squared as a function of k. And you can see that it seems to be like k squared. Of course, the range is short. But as we increase the Reynolds number, the range becomes greater. So the k squared is there. The k minus 2 is there. If we increase further the Reynolds number, we see at the end of the spectrum that our slope seems to go away from minus 2 towards k minus 5/3. And finally, for the highest Reynolds number, we see that our slope has deviated from the minus 2 spectrum towards the 5/3. So it seems that even in this case, the minus 2 comes from these strong current sheets. this is in summary all the spectra for the different Reynolds numbers. So let's see now what is the effect of the initial conditions on our spectra and on our flow. So here I'm defining the correlation coefficient in this way between U and J. And of course, at time t equals 0, this is 1. This is how we have set it in. As time evolves, you can see that this is basically for different Reynolds numbers. So this is the highest Reynolds number simulation, and this is the lowest one. The green is the lowest. So as time evolves, you can see that the large-scale velocity field decorrelates from the small-scale magnetic field. And the crosses here indicate the T peak, where the dissipation is maximum, and we have the large-scale separation. So it seems that the K-2 spectra appear as transient spectra, where there is strong enough correlations. So you can see that for the low Reynolds numbers, the correlation between U and J is strong enough, and we had this -2 spectrum. However, here was very the correlation is very small, and that's why we deviate from the -2. Here on the right-hand side, I'm plotting the correlation coefficient at these times for different Reynolds numbers, and they seem to follow a power law, which is a Reynolds number to the -3/2. And this is, let's say, how the memory is forgotten in MHD turbulence, in this case. So to conclude, the -2 power law originates from high shearing regions that manifest discontinuities in the magnetic field, corresponding to these strong currencies and not to weak turbulence effects. The initial correlation between J and U seem to create these enormous strong currencies that are not usually observed. So even though a large population, we observe a large population of currencies spontaneously formed in MHD, in this case, you had this huge currency which had the integral length scale was almost the size of the box, and the thickness of this was almost the Kolmogorov length scale. And its amplitude was strong enough to dominate the energy spectrum, as we saw. That is something that is not typically observed in MHD turbulence. And the curling of the currencies seems to modify the scaling of the energy spectrum from this -2 towards the -5/3. And of course, this happens when the JU correlations become weaker. Yeah, therefore, the debate on universality in strong MHD turbulence seems to return back to to distinguish between 5/3 and 3/2 at high enough Reynolds number, which, as we saw, even from observations, is really difficult to distinguish. So I think we need to devise different methods in order to investigate the universality of the spectra. So thank you very much for your attention. These are some papers related to the work if you are interested.
Okay, so let's go for questions. So?
In the first set of simulation you showed, there seems to be lots of symmetry.
Yes, yes.
So I think that the discontinuity are not very far from the plane of symmetry or the are the plane of symmetry.
Yeah.
Could be worrying that the shapes are due to equal symmetry.
Yes. So, okay, that's another study that we did, actually. So we, I think I have a slide. So that's true. I mean, okay. So what we did is we tried to perturbate these symmetries. So we added a small perturbation in our velocity fields. So we have a Taylor-Green flow, some small perturbation. And we try to see what is the Reynolds number that these symmetries will break. So so you can see that this is the amplitude of the perturbation. So this is 10 to the -6. You can see that the symmetries are there. Yeah. As we increase for the same Reynolds number, as we increase the perturbation, we see that this symmetry breaks, and then for higher, of course, amplitude, it breaks even further. But we see that if we increase the Reynolds number, even from 10 to the -2, they seem to break. So you really need high enough Reynolds numbers in order to break these symmetries, the Taylor-Green symmetries. And actually from asymptotics, we saw that you need 10 to the 8 Reynolds number to break these symmetries.
That Reynolds is just 1 over Q.
Sorry?
That Reynolds is just 1 over Q.
Yeah.
You mean to the symmetry is broken at 2000?
No, but this is because of the perturbation. Yeah, if you have this, if there's no perturbations, you need 10 to the 8 to break the symmetries.
That's because the symmetry, that's because the equation maintains the symmetry.
Yeah.
So that's what you're telling me is numerical noise will just
Numerical noise, yes, will grow at 10 to the 8.
Okay.
But in some of the Bouquet simulations, they preserve the Taylor-Green symmetry throughout the thing, right?
Yes, in our case we didn't because we wanted to break the symmetries. Because you cannot.
Saying that you cannot trust the spectra that come out those
No, actually you can trust the spectra because the symmetries do not break at these Reynolds numbers. So even if you preserve the symmetries, if you don't preserve them, so basically what we did is we were wasting computational time. They were saving. But we couldn't break the symmetries. We thought that the symmetries would break, but actually you need to go to 10 to the 8 to break the symmetries.
Is it related to the occurrence of reconnection? Occurrence of,
Ah,
you mentioned that.
yes.
I
Well,
would like to know.
I mean, I haven't studied this in detail, but as you see here, I mean, as you increase the Reynolds number, you can see some curling going on, and then I suppose there is some kind of instability even further, or some type of reconnection. I don't know. It might be some type of reconnection as well.
So that due to reconnection, some current sheet is in some sense distorted.
Yes.
Then this type of
Yes.
scaling change.
Yeah.
Quick question. So with this K minus 2 that you relate to the discontinuity where you have this figure, so does it really show up if you measure any higher order structure function? I mean, it's weird.
Yes.
Because when you talk about the curling and you get a K minus 5/3, so you can push the Berger's analogy even further and talk about discontinuities over a finite scale, and that will, you will get K minus 5/3
Sure.
with the same story.
Yeah.
We know that's not the case.
So basically, you get the. I think. I talked also with Anik, and she was telling me I think you will get the standard thing. So basically, this is it: P, and that's 2, and what you will get is this. So like you get in burgers.
So you get that.
So you get that, yeah. But for this case, no, not for higher.
Because then is it the usual thing, or
Perhaps, yeah,
you get
perhaps.
minus 5/3? Because then, with this picture, your curling would be something, sort of, with the Berger's analogy, it would be sort of shocks at scale L 1/3.
1/3, yeah.
With a certain probability.
Yeah.
That would give you minus 5/3.
Mhm.
I think that it shows up in your structure function.
Well, I haven't calculated it, but we think it's gonna go like that. We think, yeah. I haven't calculated it.
You said other diagnostics for MHD.
Sorry?
To differentiate between 3 and 5/3,
Yes.
definitely, like the exponents are too close. But I strongly favor that we should do flux analysis. And I believe the flux will separate out the two predictions.
Yeah. Okay.
We did for 2D way back for, they call it imbalanced chemistry.
Yeah, imbalanced, yeah. So you have cross helicity.
So the predictions are very different, which Alex said is somewhat, well, I do believe that they will be different.
Mhm.
And that should be easy to differentiate. Unfortunately, we just look at only the exponents.
Yeah. I mean, also, it would be interesting because you see what I'm doing here is I have a large-scale velocity field and a small-scale magnetic field. And you have shown then also these studies with the non-local interaction is that you have these non-local interactions between velocity fields and the magnetic field, no? UB and BU. So it would be interesting in this case to see what happens to the transfers. Because we really imposed these transfers from the time zero. So this non-locality, large-scale velocity field, small-scale magnetic field.
Are there other questions? No, let's thank the speaker.
Thank you.